Hello, everybody. It's Dr. Rehse coming to you again with another one of our fabulous DoD STEM K-12 science talks for y'all. Today, we're going to talk about a really interesting subject that actually was motivated by an actual event that I saw occurring outside my house several years ago. I want to talk about rainbows and all things rainbows, something that most people have seen up in the sky. And it turns out that very few people, myself included, don't really understand very well. So I decided to do a little digging into it. And we're going to talk today about rainbows. And next time you see one up in the sky, you're going to understand a heck of a lot more about rainbows and all the people around you. So let's go ahead and jump right into that and see what we can learn about rainbows. I'm going to share my screen here. All right, here we go. So the optics of rainbows, that's what I want to talk to you guys about, since I am a person who does optics for my job. Again, my name is Stephen Rehse. I am a professor of physics at the University of Windsor here in beautiful Windsor, Ontario, Canada. I'm the chairman of the Department of Physics here, and I'm very pleased to be talking to you all about what I hope is going to be a really interesting topic. And again, as I said, motivated by this picture that I've got on the screen right in front of you here. Before we start with this beautiful picture of the rainbow in the background, I just want to mention that, give the proper land acknowledgement here, that the University of Windsor does sit on the traditional territory of the Three Fires Confederacy of the First Nations, which includes the Ojibwe, the Ottawa, and the Potawatomi. We respect the long-standing relationship with the First Nations people in this place and the 100-mile Windsor-Essex Peninsula and the Straits of Le Detroit of Detroit. So very pleased that you're able to join with us as well. So here's just a beautiful picture of a rainbow. And this is a lot of the different phenomena that I want to talk about. And this picture comes from a really good, if you're a little bit on the younger side and you're watching this, you might want to check out this website here, the InsideThePerimeter.ca, Pi Kids Rainbows. For those of you who don't know, the Perimeter Institute is just really one of the premier institutes for theoretical physics in all of the world. And it's just located up the road from us here in Waterloo, Ontario, Canada. Their goal is nothing less than to solve the universe's greatest mysteries, from the quantum to the cosmos and all things in between. And they just have this really great site on how rainbows work, and it's geared at kids. So if this stuff that we're talking about in this lecture is just a little bit too high for you, maybe you're a little bit of a younger viewer, or you have a younger brother or sister that didn't quite understand what you were understanding, well, maybe go to that Perimeter site and go through some few more simpler exercises, because they'll be able to understand something about rainbows too. So I highly recommend that website. So as I said, this story all starts in 2012. So this is a photograph that I took outside my house. I was coming home from work one night. It was probably about 5:30, 6 o'clock. So I am looking east. The sun would be setting in the west. So it's behind me as I'm looking eastward down this street in front of me. And I saw all this really interesting stuff going on up in the skies. Of course, I saw the just brightest, most distinct rainbow I'd ever seen. But then I noticed it's got all these colors on the inside. What's going on with that? And then I noticed, oh my gosh, there's a second rainbow up there. What's going on with that? And can you actually see how much darker it is between the rainbows than it is brighter within the rainbow? Is that real? I thought, am I seeing something? Is this actually happening? I wanted to look more into it. So I tried to zoom in. This is just taken with a pocket handheld camera. So I zoomed in on that main rainbow to see all these subsidiary structures underneath. Sure enough, those are real. Wow, that's really beautiful, all that structure. I'd never really noticed that before. Here's actually the rainstorm. Of course, rainbows have something to do with sun and something to do with rain. And so here's actually the rainstorm moving through that rainbow. And you can actually see the rainfall right in front of it, where it's actually obscuring. Some of the rainbow is bright and beautiful, and some of it just being blocked by that rainfall coming out of the sky. So this was really my goal. I said, I don't really know what these things are. And I thought this will be a great STEM K-12 Saturday talk to have with you, because I want to know too. So my goal was these kind of four things. What's up with this secondary rainbow? Is it really darker in between? What's up with these? This is not a secondary rainbow, but it's some bands of color within the primary rainbow. And then why is it so much brighter in here than it is out here? What's going on with those four things? So my goal for today is if by the end of this talk, you can understand those four things, mission accomplished. So let's try to jump into that. Well, when I first started doing my research into this, I realized, yes, these are a thing, and we can at least give them their proper names. So the main rainbow that most of you see in the sky is called the primary bow. That fainter rainbow with the reversed colors on the exterior of that, that's called a secondary bow. The sky between the primary and secondary bow, turns out it actually is darker than the rest of the sky, and that's called Alexander's dark band. Who knew? And these bands of color within the primary rainbow are called supernumeraries. So these are obviously all well-known things, not to me, but they are well-known and they have names. So we've given them their proper name. So at least they have a name. And now our goal is just to kind of understand where those things come from. How is it that physics, and all of this is going to be physics and optics, of course, how do these things interact to create those rainbows, those beautiful structures that we see up in the sky? And look at this beautiful picture in the background. So the reason I wanted to give the Perimeter Institute a shout out was this initial picture that I'm using in the background with this beautiful dark sky and the super intense rainbow. This all comes from that Perimeter Institute website. Such a beautiful picture, actual photograph of a rainbow. Now you can really see those supernumeraries there. The first thing we have to understand is something in optics that we call refraction, or it's the bending of light when it passes through a material. So I'm going to go to 4 different websites today that have applets that are completely freely available to all of you. I've got the websites listed right there on the screen. So when you're done watching this talk, feel free to go to those sites and play with them to your heart's content. So this is the first one at fet.colorado.edu. That's the University of Colorado that runs some really great physics simulations. So here's that first FET website. So this is kind of a neat thing. So in this site, you've got a laser that you can move around and put wherever you want, and you turn the laser on and off. And you've got these things in this case, which are different shapes that are made up of different materials. In this case, I have a triangle of glass. So this is what we call a prism. And I'm going to press this button and turn the laser on. And by moving this laser around, I can make the laser kind of go wherever it wants. And what I'm going to do is kind of put it up here on the screen so you can see that it's just kind of hitting the edge of this box that says the environment that it's in, its air. The refraction of light just means simply this. All you have to do is notice, does this ray of light go straight through and pass through without bending? No, it does not. It hits that piece of glass. It does not go straight. It bends or changes direction. That's called refraction, the bending of light. So that light bends when it hits this first surface between the air and the glass. And it's going to, if you notice here, it doesn't go straight through. It bends again when it goes from the glass to the air. So in optics, we call that an interface. An interface is any time where the material properties changes. In this case, it's going from air to glass. It could be glass to water. It could be air to water. The primary system we're going to be dealing with coming up here in the rainbow is air to water. But anytime light hits that at a non-normal incidence, it will bend. So what I mean by that is if I hit this laser going straight on the edge here, that's called normal incidence, then it does not bend. So if it goes right flat on a surface, it will go straight through. But anytime it hits at an angle, then you can see this thing bending all over the place. All right. And if I adjust this just right, then you'll notice that for this red laser beam, which is at 650 nanometers, it's just clipping the edge of this box. So rule number 1, light when it hits a surface and it's not square onto it, meaning not normal incidence, it will bend. Rule number 2, the amount of bending depends upon the color of the light. So I'm showing you this red laser, which just clips the edge of this box up here. Let's see what happens as I change the color of that laser. Look, it's moving away from it. Green, aqua, blue, violet. Look, it's bending more and more away. The more violet or purple that color gets. And then when I go all the way back to red, it's clipping the edge of that box. So all light will bend when it hits an interface, not at perpendicular, and the amount of bending depends on the color. Those are the 2 rules of refraction that we need to know, okay? Now there's one other thing that light does at surfaces, and that is it reflects. So the light doesn't just burst through that interface, it hits it and some of it reflects off. And that's going to be really important as well, because the reflection of the light with raindrops is what's going to lead to the rainbow. So I'm going to drag this thing down. This is really cool applet. I hope you guys get to play with it when you're done. And I'm going to bring up a round drop that kind of looks like a raindrop. And instead of glass, I'm going to make it water. So this is a water droplet. And now look what happens as I move this droplet around. Some of the light hits and bends, but some of it reflects off it and reflects back at different angles. So if I kind of position this guy here, maybe something like this, you're going to see that this laser, it goes in, it reflects off the back and then bends away. this is really going to be the key to what's happening in rainbow. It's going to be these reflections that you're seeing. So I'll just jump to the chase of what a rainbow actually is. It's going to be light that is bending inside a raindrop, and so the colors get broken up because we already know the bending depends, how much bending happens depends on the color, but it's also reflecting on the inside and reflecting back at your eye. So what's going to happen is up in the sky, there's going to be some kind of sunlight, and then it's going to be reflected back to you, and you're going to see all these colors reflected back to you, which is why the sun should be at your back, because it's a reflection coming back into your eye, and that's what the rainbow is going to be. And again, so it has partly to do with refraction, because the light is bending around inside that water droplet, and bending depends on color, but it also reflects and comes back to you. So you need to understand this much optics to understand a rainbow. Reflection, that the light will bounce, so reflection is to bounce off the surface, and refraction, where it bends as it goes through a surface. And that's really what you need to understand about the physics of those things. But note that as I move this thing around, not all possible angles are always allowed. And that's going to give this rainbow this very particular shape. So let's go ahead and take a look at that. So now we understand our refraction or bending of light. So again, check out that website when you get a chance. So here's the key. It turns out that the rainbow appears as a bow and at a very particular height in the sky, because if you can trace light back to the sun and off this water droplet, the angle that those rainbow colors make with your eye will always be at 42 degrees from that incoming sunlight. So if you can, meaning you, and there's a ray, which means you draw a straight line from the sun to that water droplet, and wherever the rainbow is, it will make an angle always of 42 degrees. And this is after some refraction where the colors are splitting up inside the droplet, and one bounce off the back, and then another refraction at the other surface, and you're sitting here. So if you look at the rainbow, 42 degrees back behind you to the sun is the way that that always works. So we kind of want to understand that a little bit. So here's two kind of nice images. This is from kids.britannica.com. Again, very good images and good explanations at that site. Here's the incoming sunlight wherever this is coming from. It's bouncing off this water droplet, refracting inside, and it's reflected and dispersed on the outside, and the incoming sunlight is reflected and dispersed at an angle of 42 degrees. So if you're seeing it, it's 42 degrees from this incoming sunlight. And it turns out the secondary rainbow is always reflected and refracted at an angle of 51 degrees. So it's going to require a whole sheet of water. This is not happening off one water droplet for all this. The entire sky in front of you is full of water, so they're all acting as reflectors. And wherever you're standing, there is some particular angle where if you look up at it and look back at the sun, that'll be 42 degrees between those rays you're seeing in the sunlight, and that'll be why you see the primary rainbow at a certain point in space. Turns out the secondary rainbow, we'll get to that in a second, is actually at 51 degrees. Oh, I wonder what's up with that 51 degrees. Something different is happening with the secondary rainbow, and we're going to look at that in just a second. But first, I want to understand, why is it always 42 degrees and 51 degrees? So to do that, we're going to go to this website here first. But here's the interesting thing. Look at this beautiful, beautiful picture. You're standing here in the field somewhere. You're looking up at the sky. Obviously, the sun is behind us. The angle from your eyes up to this band and then the sunlight bouncing behind you is going to be 42 degrees. And up to this secondary bow in the sun behind you would be 51 degrees. Look how much darker it is here and lighter in here. This website has an amazing thing. And I'm going to read this from you because this is really, really important. The author of this website, this is coffeeshopphysics.com, great explanation of rainbows, said, is it actually darker in between them? It's true. The band between the primary and secondary rainbow is often the darkest part of the sky. And so this is what's really interesting. The main optical phenomena, the whole effect of the rainbow, is actually not the narrow strip of colors, which is of course what your eye is drawn to because it's so beautiful and bright and distinct. The actual optical phenomena is the bright circular disk within 42 degrees. See how much brighter it is down here? Because all that light is reflecting back at you. And the not quite as bright or darker annulus between 42 and 51, where no light can reflect back to you, because the maximum angle is going to be 42 from this one and 51 from that. So anything between 42 and 51, which is up in the sky, nothing's coming back to you. So it's all dark. Within the rainbow, it's all the colors are coming back to you, which is why it's the rain's actually acting like a mirror, and that sunlight is bouncing back at you, and it just looks like white light. Right at the edge of that zone is where, because the colors slightly refract out differently, that condition of 42 degrees is slightly different for all the different colors. So it's right at the edge of the bright zone where you're seeing these colors break up. And as this author said, the colors are just a fringe that happens along the edges of this legion of bright and dark. It's amazing how many paintings get this wrong. So actually what he's saying is the white thing and the dark thing, these are the primary things. And the rainbow is actually just at the edge of that bright thing. So this always occurs with the rainbow, but it might be so faint that you don't see it. The colors are more distinct. That's why you see it. But these things will always be present as well. You just might not notice it. So let's go to this website, Coffee Shop Physics, and see if we can understand that 42 degrees. So here it is. So here's just, again, a great picture of what's happening as you're maybe driving down the highway. The sun will be behind you. Here's a bright primary rainbow. It'll be at 42 degrees from your eyes to this thing, and then the sunlight coming in, and 51 degrees from the secondary to the sun. And it should be brighter in between and darker between that primary and secondary bow, right? It should look just like that. That's that great picture. And why is it just 42 degrees? All right, so here's a cool thing about this droplet is they're gonna see what happens. So now I can just imagine the sun is somewhere over here. So I'm just dragging this ray, and you can see how this reflection, of course, you can hit that water droplet at any and all angles that you want, but look at how the reflection goes. If the ray of light just hits the surface, it's at 28 degrees. So the reflected ray of light coming to your eye is 28 degrees, and then 35. And then at this certain point, 42 degrees, but then it starts going down again, 41, 39, 37, until, of course, when you come straight in, it goes 0 degrees right back on itself. And then if those rays of light hit the thing above it, minus 38, minus 42. So there's a maximum, but beyond it, it just reverses itself. So this is just all optics. The rainbow is light reflecting inside these little droplets of water that have to be hanging in the sky. The maximum reflected light ray, just due to that geometry of the water droplet, is 42 degrees. It's all set by optics and physics. But now look what happens if that light doesn't bounce once, but twice. Do you see over here? It punched through the surface, it reflected once, and then punched out. But what if it bounces twice inside? We call that two reflections. So up at the top, so see how it's reflecting once and then twice and then punching its way out? So up here, that light is reflecting twice inside and it emerges at 56 degrees. And then as I move it just a little bit, 52, 51, that's the minimum angle. And then it just starts getting bigger and bigger and bigger and bigger and bigger again until you can have two rays where it's out at 144 degrees. And here's actually, it goes bounces, and it goes out, which is kind of straight through, which we call 180 degrees or minus 180 degrees. But if that ray of light is hitting it down here, the minimum angle that it can make with your eyes is 51 degrees. So that's why the secondary rainbow is at an angle of 51 degrees to your eye. And that is light that's reflecting twice off the inner surface of the water droplet. And that's why it's always so much fainter than the primary, because it loses a lot of intensity at each of those reflections. So the secondary rainbow, you don't always see it. In fact, for me, I was so struck because I wasn't used to ever seeing them. They'll be quite faint because most of the light does punch through, but enough bounces off twice and it emerges at a minimum of 51 degrees. So that's why these things occur, because it's a maximum of 41 and a maximum of 42 and a minimum of 51, where no light can emerge between those. So all light comes out at all these angles, but at the maximum angle of 42, then it stops. And up here, it's at 51 and everything bigger, but it's all the angles higher and then stops at 51, leading to this thing in between, which is called Alexander's dark band. And as this website said, 5 centuries later, Alexander of Aphrodisias asked, if so, then why isn't the region between the two rainbows the brightest of all? Instead, it's darker than both rainbows. And so we call this Alexander's dark band for the ancient people who looked up at this and tried to figure out why on earth should that be so dark. So it's now we're seeing all the rules that go into making these things. 2 reflections inside a droplet to give that secondary rainbow. And the shape and the reflections of the droplets are why they occur at a certain angle up in the sky. So this is Alexander's dark band. So this is Alexander of Ephesus. He described this band in his chronicles in about 200 AD is when he was thinking about why is the sky dark in between these things. So just remember, there's always don't think that the light is just reflecting from those parts. It's kind of reflecting from everywhere. And that's why it's usually there's a sheet of rain up in front of you that makes that happen. Below the rainbow, it's reflecting and all of that light is coming to your eyes. So why should it appear dark? In this band, none of the light can get to your eye, so it appears dark. On the edges of those bands, certain colors are okay, and so that's why it breaks up into these bands, which we see as the rainbow. So how do you see a rainbow? Let's play around with the environmental conditions that actually allow one to see a rainbow, because you don't always see them. In fact, they're pretty rare, which is why they're really special. So let's go to this simulator here. So profhorn.meteor.wisc.edu for this neat kind of simulation of this thing. Rainbows, there they are. So I like this because you can, in this simulation, I can drag the sun and move it to the sun anywhere in the sky that I want. Here's you down here. I can move you around to wherever you want. We can say, are you going to see a secondary? Are you going to see the primary? You can see what's happening inside a single drop, or is it just the rain curtain, et cetera, et cetera. But the first thing you can understand is here's the sun, and look at how the right rays reflect off this rain curtain. And some of the rays of light will reflect here and some here. So depending on where you're standing, you may or may not see a rainbow. So if you're just, there's always quote unquote a rainbow, but look, if you're standing at the wrong spot, you just don't see it because those rays of light cannot reflect into your eye. But if the sun were in a different spot, boom, look, now up here, you're suddenly seeing the rainbow. But because those rays of light make a 42-degree angle with the sun, if the sun is at a certain height in the sky, look at this. If I move the sun up here, then there is no place where you can stand where you can see a rainbow because it's 42 degrees from here to here. And 42 degrees will be above the surface of the earth. And so you will never see it, which means that you may think, well, I've seen a rainbow at noon. No, you haven't. You cannot see a rainbow unless the sun is lower than 42 degrees. So these rays of light reflect off the water to your eye. And then if you're kind of standing close, it may look very low on the horizon. If you're standing very far away from where the reflection is occurring, it may appear way up high above the horizon. So they're going to look very, very different. But remember this, no matter what you think the rainbow looks like, it is not a physical thing that's right out in front of you, because it always looks like, oh, I can touch it, or maybe there's a pot of gold at the end. The rainbow is not a thing, because if you ever wonder, gee, I wonder what it'd be like to be in a plane and fly through a rainbow, you cannot. The rainbow is not a thing which hangs up in space. It is a reflection of the sunlight coming from behind you. It looks like it's hanging out in space, but it really is not. There's nothing there that you can go and touch. There's nothing to find the end of. You can't ever approach it, because as you approach it, the reflection condition changes and it kind of changes or recedes with you. So even though it looks like it's right there, it actually is not. And you can turn on the secondary rainbow here and you can see what the secondary rainbow looks like, and you don't always see that. You have to be standing in just the right spot to be getting those secondary rainbow. And of course, one thing I didn't mention that's very important is that in the secondary rainbow, the colors of light are reversed. All right, and they're reversed just due to the way the reflection happens inside that single drop. So if you pull up the single drop on this guy on these secondary reflections, you'll note that the red is coming out here and the purple here. If I reverse the primary, notice the purple here and the red there. So it's just the fact that it bounces twice, and that gets the colors reversed in the secondary from the primary. So you know you're seeing a secondary if you're seeing this thing with the opposite colors. And I think I have a really good picture of that here, right? So a rainbow will always be the primary, red on the outside, purple on the inside, but the secondary has to be red on the inside, purple on the outside, because the two reflections reverse the order of those reflections. All right, so that's that third website that I wanted to show you guys. So here's the thing, we're basically there to understanding what's going on. It is true that a rainbow can only form under the following conditions. One, the sun must be above the horizon, and it must not be obscured by clouds, mountains, or other obstacles. It means there has to be a path from the sunlight from behind you to reflect off the rain and come back to you. Just like it's bouncing off a mirror, it's bouncing off water in the atmosphere. The sun has to be quite low in the sky is rule number 2. If you're at the same elevation as your horizon, which means it's just a big flat field, means the horizon's not up above you or below you, it's just a big flat field, then the sun's altitude must be below 42 degrees, as I just showed you, to create a rainbow that can be seen from your perspective. If the sun's high in the sky, it's still reflecting. There is a rainbow to someone up in the sky, but not to you standing on the ground. It's not possible to see it because it's a reflection, and that the laws of physics are very clear on that. Number 3 rule says the air opposite the sun, as seen from your position, must be filled with a large number of water droplets. That's acting as the mirror to reflect the sunlight back to you. Rainbows always appear in the sky opposite to the sun. So if you have your back to the sun, the rainbow should be arching across the sky in front of you. The sun is passing above your head, bouncing off the water droplets and reflecting down to you. And that's why the rainbow appears this way. Last thing is, what are these bands of color inside? These things called supernumeraries. You can see these supernumeraries very clearly. 1, 2, 3, 4, 5, 6 little bands of alternating purple and green maybe on the inside. What's going on with that? Let's go to our 4th and final website to see if we can understand that. So this website is going to be this atmospheric optics. So at optics.co.uk. Just a great website for showing these things. Let me zoom in on it a little bit. Again, here, now you're understanding things. Here's the primary, here's the secondary, here's Alexander's dark band in between, here's all these supernumeraries. These supernumeraries are created by small, almost the same size raindrops. All right, and so it's actually going to come from this effect. So it turns out that all those arrows, these rays of light I was describing to you before, are not exactly right. So classical theory, which is like classical, what we call geometric optics, predicts their light always combines to make the bow brighter in that direction. But that's not actually what's happening, because light does not behave like a classical ray. We know for sure that light are waves coming from the sun. They're electromagnetic waves, but they are waves nonetheless. And the light rays undergo a lot of the same phenomena that the waves on water undergo. So when you actually do all this modeling of the reflection and the refraction through this thing, you're going to see that these 2 rays of light that come out are not actually rays of light, they are waves of light. And because they are waves, they can interfere with each other. It's called interference. Waves are doing this, and when 2 waves do that together, we call that constructive interference, and the light gets bigger and brighter. But if the waves are doing this, they're out of phase, we say that's destructive interference. They cancel each other out and you get a dark band. So the supernumeraries right on the edge of the rainbow are strictly because light are not arrows or rays, they are waves of light. And at the edge of those reflections, they're interfering with each other and creating regions of bright or dark. So it's a wave interference thing. It cannot be explained with classical geometric optics. You have to use what we call physical optics, which is modeling the light correctly as a wave. And when you get to a physics class, you're going to learn about wave superposition, you're going to learn about wave interference, and you'll learn how waves of light can interact to make positive interference, which makes things brighter, and negative interference, which makes things darker. And that's why these very subtle regions of bright and dark bands. But the cool thing is if you know your physics, those bands actually depend upon the water droplet size. So look at this. This animation actually lets me change the droplet size. So if those drops are really big, so here it says like 1.5 millimeters in diameter, you almost can't see those supernumeraries at all. And as the water droplets get smaller, now I'm down to like under 1 millimeter, 0.86 millimeters. Look how those supernumeraries start to form. So it's always going to be at that same location in the sky, 42 degrees. But as the water droplets get smaller, more like mist, look at how that interference becomes more distinct. So if you see the supernumeraries, that's telling you something about the water droplet size, which is again why you don't always see supernumeraries, because if it's just huge, big water droplets, you're never going to see them. But if they're very small, fine water droplets, the smaller they are, the more pronounced those supernumeraries will be. So it's a wave interference effect, and it has a little something to do with the actual size of the water droplets up in space, up in the air, floating in front of you. So that's a really cool thing about the supernumeraries. So explaining these things, pretty easy. You just have to say, look, light is not a ray, it's a wave. And when those waves interact with each other as they emerge from that water droplet, there's just going to be regions where they interfere, and that creates the supernumeraries. And that interference only occurs for waves, not ever for rays. So this is, again, more proof that light actually is an electromagnetic wave, not any kind of ray or arrow. It just doesn't work that way. All right, so I think that's it. I think that's all for today. I've given you guys lots of stuff to think about, and I've given you all the tools now to go and explore on your own. You should now be able to understand why a rainbow appears at a certain angular height in the sky. You should be able to kind of explain why there's a dark band outside that primary bow and why there's a secondary bow beyond that. Why is it brighter on the inside of a rainbow than it is on the outside of a rainbow, which should be dark, which is Alexander's dark band? If you see the supernumeraries, what is causing those? What's making all those happen? So our quest was today to try to understand and explain all of those things. And I think we've done a pretty good job. So that's all for today. I thank you very much for listening. I hope you can look up at the sky next time you see a rainbow, maybe spend some time telling your entire family about what you think a rainbow is, because it's a really, really interesting physics topic. So I appreciate you spending some time with me today. And with that, I think I will stop for today. I'll stop my sharing here, and thank you all very, very much for spending some time with me. Have a great day, everybody. Bye.